Today we've got a real treat for you. That's called line integrals. So you may have heard of this idea from physics that work equals force times distance. So if you were to take an object from this point, let's say that it's going to be this pen right here, from right there. Oh, pen, please cooperate. Anyway, so you take this pen and you're going to drag it across the page. So of course the pen's not that heavy, it doesn't take that much work, but you could add up the work as it goes along. So that would be if it was an actual straight line. So you could take this and you then could divide it into, say, 1-inch pieces, and then for every 1-inch piece you could find out how much force was required, and then you multiply by that distance, so however much force times that inch, however much force, etc. Add them all up, and that's the total amount of work. But of course, you don't just have to move something in a straight line. You could move it like this. So that's in general what it is. So even though it's called line integral, it really should be called curve integral. Suppose that you've got this curve. So in other words, I dragged the pen along this curve right here. Then create the line integral. Well, first of all, we need the parametric functions for this C curve. So let's say it's x equals a function of t and y equals a function of t, where the t ranges between a and b. And that's what causes it to go from there to there. Now we'll have another function like the force function. So now we're going to integrate this function of x and y along the curve C. Well, there's actually 3 ways to do it, because as I'm moving from here to here, I moved not only to the right, but I also moved up. So it could be that you want to add up everything along the curve, or perhaps just the motion to the right is what's important to you. In other words, in the x direction, or that amount of work that's being done when you go up, that would be in the y direction. So there's actually 3 types of line integrals. So there is, first of all, if you just integrate over the curve C, the function, and then this is going to be ds, which represents over the distance, s being the distance. So then we're going to integrate from a to b for these limits right here. And then x and y both need to be replaced with the g and the h. So we're making this a function of t. So substitute the g function, substitute the h function. And then we would need to know the length of this. And so you may remember, to find arc length, that is the square root of each derivative squared. So then take the derivative of g and square it, plus the derivative of h and square it. And then it's going to be an integral with respect to t. Now, if you just want to know what's going on in the x direction, then this is going to be dx. So it's basically going to be the exact same thing, except we're only going to be using this part. Which means, so this is just gone. We're not even using the y part here. And so once this is gone, the square root and the square are going to cancel each other out. So it's going to be the integral from a to b, then change it over to a function of t. So you do need to use both parts and replace the x and the y, so it's a function of t. And then this part is just going to become times the g prime, and then dt. Likewise, if you only wanted to know information in the y direction, then it's going to be almost exactly the same, except we're going to just be using this part. And then the square and the square root will cancel each other out. So it's times h prime. All right. Then for the first example. Example number 1. Part A is going to be integrate over c, and the function is x times the square root of y dx. And then for the next part, we'll do dy. And then c, I'll put it over here, where c is defined by x is equal to 2t plus 1, y is equal to t squared, and this is for t going from 0 to 5. So we're going to need to know dx. So dx is derivative right here. That's going to be 2 times dt. And then we just need to substitute what x equals right there, substitute what y equals right there. So we're changing it over to a function of t. So that will be 2t plus 1 times the square root of t squared, and then multiply by what dx equals, so multiply by 2 dt, and then integrate from 0 to 5. So I'm going to do some algebra first. This is just t, so when you distribute it, there's going to be 2t squared, and then this times this will just be t, and this little 2 right here, I could just factor it out. So doing the antiderivatives, this one's going to be 2t cubed over 3 plus t squared over 2. And then it gets evaluated from 0 to 5. So that's going to be 2, and then 2 times 5 cubed over 3 plus 5 squared over 2. And then the 0 will just mean minus 0. So how much is this? So we've got 2 times, and then there's a 2 times 5 is cubed, and that's divided by 3, plus this would be 25 divided by 2. So it equals 191 and 2/3. Now, what's the difference if you put dy right here? So do the same integral, x times the square root of y, but then what if this was dy? So we first need to find out what dy equals. So dy is equal to 2t dt. And then change this to a function of x. So replace the x right here. So x gets replaced with 2t plus 1. And then the square root of t squared. And then we need to multiply by the dy. So that's going to be 2t dt. And then integrate from 0 to 5. So again, do some algebra. This is going to be t times this is 2t squared. So I'll take the 2t squared and multiply it through. So 2t squared times 2t is going to be 4t cubed. And then 2t squared times 1. Now that we're done with the algebra, it's time to find the antiderivative. So the antiderivative of this is just t to the fourth. And then this one will be 2t to the 3 over 3. And then that gets evaluated from 0 to 5. So it's going to be 5 to the 4th plus 2 times 5 to the 3rd over 3, and then minus 0 from this. So how much is that? So 5 is raised to the 4, and then plus 2 times 5 is cubed, and divided by 3. So it's 708 and a third. Now off to example number 2. So for example number 2, it's just going to be set up the integral. And we're going to be integrating over the curve C, x squared times y to the 5th ds. So to make the problem a little more interesting, you aren't given the function itself, but instead given a picture, and then create the function. And the picture looks like this. So the curve C, so the object moved this way first, and then it went this way. So that whole thing is the curve C. And it's going in this direction. And the direction matters, because whether you go forward or backward, different things can happen. So we need to have it going in the correct direction. So I'm going to break this up and say this is curve number 1 and this is curve number 2. And then you could integrate over curve 1, integrate over curve 2, and then add the two together, and that will be integrating over C. So for curve 1. Well, for this one right here, x is always equal to 1. And then the y value ranges from 1 to 3. So then I could say y is equal to just t, and then t is going to range from 1 to 3. And because I have it starting at 1 and ending at 3, that means it's going to be going the correct direction. It's going to go from y is a 1 until y is a 3. Then what about curve 2? So this is a line, it's got negative slope. So let's see, the slope would be rise is, actually it's a drop. So it's going to be, it went from 3 down to 1, so it dropped by 2. And then this is a run of 5. So there's its slope. And then we could find out just using good old algebra 1. So I could use this point right here, which is the point 6, 1, and go y minus the y value of 1 equals the slope times x minus the x value of 6. So this is going to be negative 2/5 x and then plus 12/5. And then add 1 to both sides. So y is equal to negative 2/5 x. That'll be 5/5 plus 12/5 is 17/5. So to make this line right here, what I could do is just say, let x equal to t, and then y will equal this times t plus 17 over 5. So let x equal t, and y equals negative 2/5 t plus 17/5. Now, what do I put for the limits on t. So at the beginning, it's at this point 1, 3. So right here, x is a 1. So if I put a 1, that's going to work. If I put a 1 right here, that means it's going to be 17 fifths minus 2 fifths. That's 15 fifths, and that equals 3. So that point is correct. And what about over here? Oh, so I forgot to write that down. So that means t is going to go from 1 until... So what does t equal over here? So over here, x equals 6. So that would say that t equals 6. Now I want to make sure that it works, because at this point, then the y value should equal 1. So if I plug in a 6 right here, I should get y equals 1. So if you plug in a 6, this will be negative 12 fifths, and then plus 17, negative 12 plus 17, that's going to be 5 fifths, which is 1. Okay, now that part's set up. Now, remember that the first formula means we need to do this. Take each derivative, square it, add them, and put a square root. So we're going to need to know each derivative. All right, and we're going to need to do it for each curve. So for curve 1, so the derivative of x, so the derivative right here, that's going to be 0. The derivative of y is equal to 1. So now it's going to be integrate, and the limits for curve 1 are from 1 to 3. And then we need to use this part. So the x is going to get squared, and the y is to the 5th. So the x is going to get squared, and the y is to the 5th. And then multiply that by the square root of 0 squared plus 1 squared from dx and dy, and then this is going to be dt. So then this one is set up. Let me just clean it up a little bit. That's just going to be a 1. That's just a 1. So it's actually just integrate t to the 5th. And there we go. Since it said set up the integral, I'm now done with that one. Isn't that ironic? The easiest problem there is, and we're not even going to integrate it. Now, what about, so this is example number 2 still. Now, what about for C2? So we need the derivative of x. That's going to be a 1. We need the derivative of y. That's going to be a negative 2 fifths. And then integrate from, for this one, it's 1 to 6. And then it's going to be the x gets squared, and the, oops, I meant to put t. The x gets squared, and the y is raised to the 5th. And then we need to square each one of these, add them together, and put it inside a square root. And then that one's set up. Although I really feel like I should clean this one up a little bit. This would be 4 25ths plus a 1. So that's 25 25ths. So in total, that's 29 25ths. And when you take the square root of 29 25ths, it would look like this. And then this part just stays the same. There's not really any algebra that I'm going to do to this one. And now I am glad that it said just set it up, because I don't really want to, oh, this is to the 5th. I don't really want to have to multiply all of this out and do 10 minutes of algebra. Okay, so that's set up. And then for example number 3, we're going to evaluate the integral over c and then it's going to be x squared plus y squared dx. And then add to that the integral over c of x times dy. And this is c. It's a circle of radius 1. So the first thing we need is a parametric function that will give you a circle of radius 1. Well, because sine squared plus cosine squared equals 1, then a good choice would be x equals cosine of t, y equals sine of t, or you could switch the order on these and that would be fine also. They both give you a circle of radius 1. And then because we need the whole circle, the t is going to go from 0 to 2 pi. Okay, so we're going to need dx and we're going to need dy. So dx is equal to, the derivative of x is negative sine of t. dy is the derivative of sine, which is cosine. And then set this up. So we're going to change this over to a function of t, which means that the limits are going to go from 0 to 2 pi. And then we need x squared plus y squared, so that's going to be cosine squared plus sine squared. And then that gets multiplied with the dx. And then we need to add to that the integral from 0 to 2 pi, and then it's just x times dy. So over here, cosine squared plus sine squared is just a 1, so all we really need to do is integrate negative sine. So that's going to be cosine of t. And then that part gets evaluated from 0 to 2 pi. Then this one is cosine squared, so for that I need to use the trig identity that it's 1 plus cosine of 2t over 2 from 0 to 2 pi. Okay, so this one is going to be cosine of 2 pi minus cosine of 0. And with this one, I could factor out the 1/2. The antiderivative of this 1 will be t. The antiderivative of cosine is sine. And then because of the chain rule, this one needs to be divided by 2. And then evaluate from 0 to 2 pi. So finally, this part is going to be 1 minus 1 is 0. And this part is going to be a 1/2 times, you substitute the 2 pi, and then this will be sine of 4 pi, which is 0. Then substitute the 0, which is 0, and sine of 0, which is 0. So finally, all there is 1/2 of 2 pi, so that is pi. Next up, we're going to use this idea from physics that work is equal to force times distance. So let's say that this is the force function. Capital F for force. Now in the previous examples, we were dealing with things in 2 dimensions. So the idea is that some object was going around this circle, which is in 2 dimensions. But then let's say that this, like this pen, is in 3 dimensions, and I'm doing a lot of work by moving it around in 3 dimensions. So this force function has to be in 3 dimensions. So let's say that m is going to be the first component, and n is going to be the middle component, and p is going to be the last component. And then this is a function of x and y and z. is like the pen. It's in 3 dimensions, so it's got an X, a Y, and a Z. Now that's going to be the force, and then you need to take it along some path. So let's say you go along a path C, which is defined by, and then this also has to be in 3 dimensions. So X is going to be G of T, and Y is going to be H of T, and Z is going to be K of T. So then the total amount of work is going to be integrate along the path C, m times dx, because m is the x information, so this is measuring how much work is being done in the x direction, and then n times dy, so that's going to give you the amount of work in the y direction, and then p times dz, the work in the vertical direction. Or there's a slightly different way to look at it. So you could just abbreviate this by saying force is equal to this vector, m, n, p. And if you let r be this vector, x comma y comma z, so it basically just gives you your position. Then look at the derivative of r. So that would mean take the derivative of x, take the derivative of y, and take the derivative of z. And then what is this compared to this vector and this vector? So you just take the dot product of this vector and this vector, and that would mean m times dx plus n times dy plus p times dz. So in other words, work is equal to the integral of f dot dr. That's something that physicists really love to do, is take formulas and break them down as small as possible. What's the least number of letters I can use? So for example number 4. So the force is given by this vector. It's e to the x, e to the y, e to the z. And then it's along this path. So x is equal to t, y is equal to t squared, and z is equal to t cubed. Now, as I just said, there's this shortcut. There's this little shortcut formula. And in that case, r is equal to x comma y comma z. But I just wrote down what x and y and z equal. They equal these guys right here. So let r equal the x, which equals t, the y, which equals t squared, and the z, which equals t cubed. And then find the derivative. So then dr is going to be a 1, a 2t, and a 3t squared. So work is equal to the integral of f dr. So take the dot product of this with this, although we need to change this over so that it has t's in it. So f is going to be e to the x, which means it's e to the t. The middle component is e to the y, so that's e to the t squared. And then the last one is e to the z, so that's e to the t cubed. And then dot product that with the dr. 1, 2, 3t squared. And now it's going to be with t. And you know what? I think I forgot to write down over here that it's given that t goes from 0 to 1. So this should go 0 to 1. So now do the dot product. So the first one times the first one, that's just going to be integrate e to the t plus the middle times the middle will be 2t times t squared. And then the last one times the last one will be 3t squared times e to the t cubed. And then integrate all of that with respect to t going from 0 to 1. Well, the antiderivative of e to the t, that's just e to the t. And if you do u substitution on this one, u will equal t squared. The derivative, that's a 2t, which is exactly what's showing up right there. So this would just become integrate e to the u, which means it is e to the u. And the same thing happens right there. If you do u substitution, the du is sitting right there. So integrate this one, it would become e to the u, or in other words, just e to the t cubed. And then evaluate from 0 to 1. So this would be e to the 1, e to the 1, e to the 1. So we have 3 of them that are e to the 1. Minus, when you substitute the 0, e to the 0 is a 1, plus another 1, plus another 1. So the final answer is, you got 3 e's minus 3.